Good afternoon, ladies and gentlemen. Welcome to I²CNER seminar. My name is Shintaro Ida in Hydrogen Production Division. Today we have special guest, Professor Richard Glass in the Department of Chemistry and Biochemistry at University of Arizona. First, I would like to shortly introduce Professor Glass. He got PhD in 1967 at Harvard University. His main interests are organoiron and chalcogen chemistry and the chemical biology of selenium and their impact on energy research, material science, and biological redox states. And he is a fellow of the American Association for the Advancement of Science and a member of American Chemical Society and the International Society of Heterocyclic Chemistry. And he is a member of the International Committee for the International Conference of Heteroatom Chemistry and the International Symposium on the Organic Chemistry of Sulfur, and on the editorial board of the Journal of Sulfur Chemistry and Archivoc. And he served on the governmental panels and industrial consult. So it's my great pleasure to chair his special lecture. The title of his talk today is Biomimetic Diiron Catalyst for Hydrogen Production. Professor Glass, please.
Well, it's a pleasure to be here and to have this opportunity to talk about some of our research in developing catalysts for hydrogen production. It's especially rewarding for me to be in one of the centers in the world for hydrogen studies, and the work you're doing here is actually very fascinating. What I will show you is our efforts to generate molecular soluble catalysts that will catalyze both the conversion of electricity, electrochemical energy, into storable chemical energy as molecular hydrogen, as well as our hopes in the future, although I won't be describing any of this work, to convert solar energy directly into molecular hydrogen. So this is just a maybe bringing coals to Newcastle. Some background that you're, of course, familiar with here, but perhaps it'll help you to see what our motivation is if I give you some of the reasons that we're doing what I'll describe today. So, as you know, the world energy demand, this is an estimate that comes from the International Energy Agency, for energy is going to greatly increase. In 20 years, it's going to go up substantially, perhaps 60%, based mainly on the exponential growth and demand for energy in both China and India. The rest of the world will go up gradually, but nothing like the explosive growth demand in China and India. This blue line are the members of the International Energy Agency, Europe, the United States, and so on, that prepared this estimate. It's also been said, and it's at least historically interesting, that if you look at the major source of energy, petroleum, oil, that there is going to be a peak in the production of oil. And here we have the time scale, and here we have the production of oil. And it was expected to peak, that is, conventional sources of oil or petroleum were expected to peak at 2010. That didn't happen, probably mainly because of the downturn in the economy. But there are other factors that we'll talk about concerning the production of oil. But the estimate was that there was going to be a peak, and then it was going to decrease. And so that meant in 20 years, there was going to be a substantial shortfall. So how is this shortfall going to be met? And here are the primary sources of energy. As already mentioned, oil is perhaps the major one. And in the category of fossil fuels, we also have natural gas, mainly methane, by the way, and coal. These eventually will run out for sure. They're non-renewable. There also is nuclear energy, and nuclear fission is a rather controversial one. Japan used to get 30% of your energy from nuclear fission. All the plants have been shut down in Japan after the tragedy in Fukushima, and each time after that, each time a plant would be serviced, it wasn't started up. There may be a change in that. In OE, I understand that the council has agreed to start up the nuclear plant. They're waiting for the mayor to agree. But anyway, that's a political issue. Nuclear fusion is an excellent way to get energy. Unfortunately, the big problem, as you know, is containment. There are experiments that are planned, but to get sustainable fusion events, being able to contain that fusion is still a major problem. Perhaps, in a way, the most exciting possibilities for meeting energy demands are renewable energy. They'll last forever, in principle, and so that's a great attraction for these. And some of them are just listed here: solar photovoltaic, wind. So you actually are using some windmill generators here. And so on. Biomass I'll mention because it suffers potentially from the same problem as fossil fuels. It's renewable, but when you burn it, you get CO2. All of these, when you burn it, you get CO2. And that creates another major problem with these fossil fuels, and that is CO2 is a greenhouse gas, as you know. It contributes to global warming. And so we'd like to move away from these for the sake of the environment. Biomass is said to be CO2 neutral. That is, the way you get biomass is you fix CO2 in biological matter, and then you just burn it and get the CO2 back. And so as long as some of the CO2 doesn't escape, it would be neutral so far as CO2. Shown here is the projection for the next 20 years or so for what will be used as the sources for this increase in energy demand. The first thing you'll notice, this is oil. And oil, rather than peaking, is going up. And the reason for that is really threefold. The peak oil was based on the known oil wells that were being produced and the known reserves of oil. There have been new discoveries in the deep ocean. Brazil has been very active in drilling in the deep ocean, in the Arctic. But even more interestingly, alternative sources of oil. So these are the tar sands in Alberta, and also shale oil in the United States and elsewhere, in which one uses fracking to release this competitively. So these new sources of oil are the ones that are going to be responsible for this increase. You'll see a substantial increase in coal. And the reason for the increased use in coal is that both China and the U.S. have a lot of coal. So when you need energy, if the prices of petroleum are going to go up, there may be a political decision to go to coal. And the United States is called, by the way, the Saudi Arabia of coal, meaning that we have so much coal reserves, it's like Saudi Arabia with petroleum or oil reserves. Gas is also going to increase, but as already mentioned, partly due to fracking, that also releases gas. And I might mention parenthetically an interesting one that has just been suggested is methane forms hydrates with water at high pressures and low temperatures. So in the ocean, and also in the tundra in Russia, there are methane hydrates. And it was first worried that what would happen is when global warming increased, there'd be a tipping process because these methane hydrates would dissociate, release methane, and methane is an even more potent greenhouse gas than CO2. Now what people are saying is, well, let's mine the methane and use it in order to meet energy needs. What is unfortunate is you'll notice here the renewables are only expected to make a relatively modest contribution to the increase in energy needs. And that's a problem because, as I say, the major worry is the increase in global warming as a result of the increase in CO2. So what we'd like to be able to do is, or what we think, is that if we can go to hydrogen, hydrogen is not a primary energy source, but if we could use hydrogen as an energy source, that would be very attractive. And if one can convert electricity from, say, photovoltaic cells into hydrogen, that has a number of advantages. I might say solar photovoltaics are perhaps an excellent technology that is being heavily developed around the world, in the U.S. in particular. And the idea here is that you're really converting solar energy into electricity. And solar energy, there's enough solar energy per day to meet the world's energy needs for a year. But there's several problems with solar energy. It's diffuse, that's the whole world. And the solar photovoltaics don't work at night or on a rainy day or a cloudy day. So it'd be nice to convert that electricity into something that's storable, that you can then get the energy back whenever you want. And hydrogen might be a good solution, we think, for storing electrical energy as chemical energy. Alternatively, one can imagine, as I already mentioned, directly converting solar energy into chemical energy as hydrogen. So the way hydrogen is made now is shown here. This is these are the commercial ways for making it. As I mentioned, methane, natural gas is mainly methane, some other hydrocarbons as well. And this process, steam reforming, is the way to make hydrogen. And you can also use the water-gas shift reaction to make hydrogen. This is the commercial sources. Obviously, electrolysis of water, as you do in the hydrogen station here, is another way that has some problems with it. But this is the commercial sources. This is expensive. I was amazed to find that the most expensive part, the biggest cost in hydrodesulfurization of petroleum. So Europe insisted that all the sulfur be removed from the petroleum from the Middle East that's shipped to European markets. And so hydrodesulfurization is used. One takes hydrogen, a molybdenum cobalt sulfide catalyst, and removes all the sulfur. The most expensive part is the hydrogen for that process. It's been suggested that one could use methanol as a liquid fuel. It has some attractive properties. It's a liquid. It should be relatively easy to handle. But the difficulty here again is that if you burn it, you're going to get CO2. An old way of making chemical bonds from which you can get energy from if you want, or synthetic petroleum, is the Fischer-Tropsch reaction. So the reason that one wants to use hydrogen is that if you burn it to get water, you get a lot of energy. If you make it from water, it's recyclable, and no CO2 is involved. So there are a whole bunch of other details, which I'm not going to go through, but I would point out that you don't want to burn it. And as you well know, it's if you burn it, as in a car, let's say an internal combustion engine, you're limited by the Carnot cycle. So it's a heat engine, and it's never going to be as efficient as, or have the potential for being as efficient as a fuel cell. So here, just quickly diagrammed a fuel cell. The important points I want, you'll see in a moment, and that is hydrogen comes in one side, and then we have an electrode here. Electrons are stripped off from the hydrogen, and they go into this circuit. That leaves protons, which go through this semi-permeable membrane, and typically Nafion. And at the other side, one has oxygen or air come in. The electrons come and are added to the oxygen. It gets reduced, gets protonated to generate water. So overall, we're indirectly using hydrogen and oxygen to get water. And the advantage of the fuel cell is not limited by the Carnot cycle, so it could have a much greater efficiency than an internal combustion engine. The problem with it, and I might say, as you know, this is not pie in the sky. They've been developed by NASA in the Apollo space program, but as you might well expect from the space program, the costs are astronomical. So the reason it's so expensive is if you look at the electrode here, when you take the electrons away from the hydrogen, the catalyst is platinum. If you look at the other electrode, when you add the electrons to oxygen, again, we're using platinum. And platinum is expensive and it's rare. That is part of the problem with this technology. Nafion also is expensive, by the way. A number of people are working on improvements or other less expensive semi-permeable membranes. Now, you know this because you see this, I guess, once a week, I understand. But here's an example of a commercially used fuel cell in a hydrogen bus. And so the tanks are up here, the fuel cell here. It's used to drive the bus. But again, you'll recognize it's expensive. It's a Mercedes-Benz, so this is not cheap technology. I now have a picture. You don't need to see the picture of the hydrogen fueling station here, but this is a hydrogen fueling station in Iceland. Iceland was very interested in developing hydrogen as a fuel because they have all this geothermal energy where they use that to drive electrolysis of water to have to generate hydrogen at these fueling stations. So this then just shows the electrolysis of water. This is relatively, again, typically platinum is used, relatively inefficient technique. One can use, instead of electricity, one can use sunlight to drive the reaction. We're actually interested in this, but at present, people are studying that, but there's still a lot of work to be done. Actually works fairly well for generating oxygen. More work needs to be done for generating hydrogen, although here you're famous for being able to do both, to split water and get hydrogen and oxygen. And this would avoid these other more expensive technologies that we've said. This just shows you, so far as photovoltaic cells or solar cells are concerned, that the efficiency can be quite high. Spectrolab, which is a subsidiary of Boeing, has claimed to, and it's been validated, get 41% conversion of solar energy into electricity using these multi-junction cells. The problem with these multi-junction cells is they use rather exotic elements. This is gallium and indium, for example. But nevertheless, this shows that one can greatly increase the efficiency of solar cells. Now, nature has long converted sunlight into stored chemical energy, chemical bonds, by photosynthesis, as shown here. And essentially, chlorophyll absorbs light, water is split, and the electrons and protons are used to reduce NADP to get NADPH, which is used to fix CO2 to make sugars, glucose initially, but sugars in general, to store the energy in carbon-hydrogen bonds, and then when it needs the energy, it metabolizes the carbon-hydrogen bonds. It's even known that some algae can convert sunlight into hydrogen using an enzyme appropriately named hydrogenase. So what we'd like to do is develop a catalyst that's going to be cheap, a replacement for platinum, efficient, and long-lasting, robust, and readily available, so that we can reduce protons, hopefully from water, to give hydrogen, and then perhaps these catalysts will work in fuel cells to, when desired, convert the energy stored chemically into water and energy. So this is our water. This will be recyclable if we use water to generate the protons, or the protons from water. And this then is recyclable, renewable, using water. It's good for living plants. This is an advertisement for Arizona. This is the giant saguaro, the John Wayne cactus plant that our region is famous for. So here is sort of a schematic of what we want to do. We're going to have an electrode where we're going to have electrons react with a catalyst to generate a reduced catalyst that's going to catalyze the production of hydrogen, the reduction of some acid, hopefully eventually water, to generate hydrogen, go back and be able to convert electrical energy into chemically stored energy as hydrogen. This is an electrochemical cell, and we can monitor this by looking at the reduction of our catalyst and then whether we catalytically produce hydrogen. So that's the overall plan. And the question is, how do you develop a new catalyst? And one of the challenges for chemistry in the 21st century is to develop new catalysts ab initio. And we don't know how to do that. Unfortunately, that's something for younger people to investigate and solve. But what we do is we get help from nature. And that is, there are enzymes, I already mentioned this, hydrogenase, that catalyze the production of hydrogen from water. And these enzymes have been isolated and their crystal structure is determined. And one of the interesting features about them is that they're typically bimetallic. There are actually 3 classes. One has 2 irons at its active site. Another one has iron and nickel, the second class. And the third class is relatively rare. It has one iron at its active site, and it's somewhat specialized. These, I might say that you might be surprised to know that you produce hydrogen. And that's the reason for that is that you have in your intestines some anaerobic bacteria which typically produce hydrogen. Here's an anaerobic bacteria, Desulfovibrio desulfuricans, that has hydrogenase I'll talk about in a moment, and it's an anaerobic bacteria. So these bacteria live in colonies in which there's no air, no oxygen, and they place their electrons in chemically stored hydrogen, make molecular hydrogen. Other microorganisms take that hydrogen, take the electrons out, and react them with nitrate or sulfate. And they live in that way in symbiosis, so they can store electrons, electrical energy, if you like, and get chemical energy back out by reducing nitrate or sulfate. So the enzyme that's found in that organism, the hydrogenase, is shown here. There's the active site, and all this represents the proteins around there. Here's a blow-up of the active site. There are 2 irons. One of the attractive things about this is iron is cheap. It's one of the most abundant metals, and so it will be a lot better than platinum. It's readily available and cheap, not rare and expensive. Another feature about this is that this particular active site is found buried in the center of this protein. So one of the questions comes, how do electrons get in and out? And you'll notice there are these Fe4S4 clusters. They're redox clusters. So if you have a reducing agent here, it'll send an electron in. This is essentially wired to the surface, and hydrogen will come bubbling out. This enzyme is among the most efficient enzymes known. It produces 6,000 molecules of hydrogen per second per active site. Furthermore, it does this with relatively low overpotential. That is, it's more or less the thermodynamic potential for generating hydrogens from protons or from water. Another thing that attracted us to this enzyme is that this is the active site. It's very simple. It has a couple of sulfurs bridging the irons. It has this 3-atom bridge. It was initially believed that was a CH2, but now most people believe it's NH, and there's evidence for this. It could also be an oxygen. At the resolution of the X-ray structure for the enzyme, you can't distinguish that. But what's unusual about the enzyme is it's organometallic. It has a metal-carbon bond. And that turns out to be, prior to this, the only organometallic enzyme was vitamin B12. And so that made it rather interesting, but also it has CO and CN ligands. How do they get in there? Organometallic chemists, if they want a CO ligand, they bubble in carbon monoxide. You want a cyanide ligand, add potassium cyanide. They'll both kill living things. So the biosynthesis of this is kind of interesting. From our perspective, as you'll see, what I also want to point out is the geometry about this iron center, and that there's a bridging carbonyl. So in any event, one could make things that look a lot like that active site. Now, we'll talk about making those in just a moment, but let me point out one feature that I mentioned with the enzyme. It has essentially no overpotential. Now, often catalysts are going to require more negative potentials than the thermodynamic potential, and that is to say an overpotential, a more negative potential than is needed thermodynamically, and that's a waste of energy. So with our compounds, the compounds that we've looked at, we look at organic solvents. They're soluble in that. They're not soluble in water. And so we want to know what the thermodynamic potential is in organic solvents, particularly acetonitrile. Here's the thermodynamic potential we're interested in. It's a combination of the hydrogen potential, but also the protons that are reduced come from the acid. So the pKa of the acid is involved. So it's very easy to calculate what the potential E0 is going to be in, say, acetonitrile. If you know the pKa, you can calculate E0. And the one I want to focus on is acetic acid, because that's the one we're going to be using. Its pKa is 22.3. So the E0 is about minus 1.5. That's the thermodynamic potential versus ferrocene-ferrocinium as the reference electrode. Acetic acid in water has a pKa of 4.7. It's almost 18 orders of magnitude weaker acid in acetonitrile. So we're interested in using weak acids, not strong acids, and ultimately, as I say, water. Here's the material we're interested in. You'll notice the 2 irons that we've made and studied. Sulfur is bridging the 2 irons. And over here, we have a bridge that involves an aromatic ring. The reason for that is we thought the pi system would help communication and make this a better catalyst, or at least a good catalyst. And it's relatively easy to make, as shown here, from 1,2-dithylbenzene and Fe2CO9, which provides this. Alternatively, another system, another way you can synthesize it, is from FeCO5, And FeCO5 is very cheap and readily available. Sulfur is very cheap and readily, this is elemental sulfur, very cheap and readily available. In fact, people probably pay you to take it away. There are big piles of it in the Middle East that they want to get rid of. And base, Heber in 1937 showed you can get this beautifully crystalline disulfide. And this was studied by Dietmar Seyferth in great detail. And it reacts, he called it an inorganic disulfide, meaning it reacts just like an organic disulfide. You can reduce it, make a dithiolate, protonate, make a dithiol, alkylate, make bridge systems. Very easy to react it here with 1,2-diodobenzene to get the catalyst that we want, that we were interested in studying. So it's readily easily made from cheap starting materials, and that was an attractive feature. Shown here are cyclic voltammetric results. So what we're doing here is scanning the potential in more negative directions, monitoring cathodic current in this direction, anodic current in that direction. So with that compound I showed you, as we go to more negative potentials, we see a reduction, and continue out, nothing happens here, return, we see the oxidation of that species. There are two things that are interesting about this. Number one, the reduction is reversible. That means the species you produce by adding electrons is stable. You can reoxidize it. Number two, this is a 2-electron reduction. To generate hydrogen from protons, you want 2 electrons, so that's a good thing. But what's surprising about that is it's very rare. And the reason it's rare is, if you think about it, if you have something that's neutral, no charge, you add an electron to it, has a negative charge. To add another negatively charged electron, you'd expect that to be more difficult because of electrostatic repulsion, Coulombic repulsion. And here, it's at least as, it's at least as easy or easier to add the second electron. That's called potential inversion, and we're very interested in that, why that occurs, as you'll see. So now we add acetic acid. Now, if we didn't have a catalyst, we'd see no reduction of acetic acid. We're not in the range where we would get direct reduction of acetic acid. Now when we scan the potential, we see a new peak. And with acetic acid and our catalyst, more acetic acid, bigger peak with more acetic acid, same amount of catalyst, 50 millimolar acetic acid, enormous amount of current is flowing. Hydrogen is being produced as a result of this, and so we're getting catalytic hydrogen production. So the good news is it's very efficient. The bad news is you'll notice the potential is -2. And for reduction, the thermodynamic potential for reducing acetic acid, as was pointed out, is -1.5. So about a half a volt over potential. Shown here is the theoretical simulation of these curves using DigiSim for those who might be interested. This shows our electrode, this is the solution. And as we're doing the experiment, these are bubbles of joy. These are hydrogen bubbles being formed. Hydrogen is being produced so fast, we can actually see bubbles of it. And we analyze this for hydrogen. We know it's hydrogen. So it's very efficient hydrogen production. In fact, with acids slightly more acidic than acetic acid, the rate determining step in hydrogen production is diffusion to the electrode surface. So as I pointed out, this is a really efficient catalyst, but it has a half a volt over potential. How can you improve the catalyst? Well, there are several ways to do this. And one way is if you knew the mechanism by which this catalyzes hydrogen production, you might be able to improve the slow step or the difficult step, or the step that requires the -2 volts. So you can, whenever you're trying to determine catalytic mechanisms, you can try to trap intermediates. You can try to determine intermediates spectroscopically. Typically, these are very difficult experiments, very time-consuming. So we resorted to calculations. There's good news and bad news here. As long as the system converges, you get an answer. That's the good news. The bad news about calculations is the answer may be all wrong. So the first thing we wanted to do is validate our calculations. We use DFT, density functional theoretical calculations. For those who are interested in the details, they're here. But anyway, using this computational method, these are the calculated values for various molecular parameters. This is the X-ray crystal structure, the experimental results, and you can see they agree very well. An even more stringent test is shown here. When you have a metal carbonyl, you can look at the carbonyl stretching frequency, and that depends very stringently on the geometry of the system and the electron richness of the metal because of back bonding. So shown here is the infrared spectrum in the metal carbonyl stretching frequency for this catalyst. Here are our calculated metal carbonyl stretching frequencies. You can see there's an excellent match. This means we got the geometry right. This means we have the electron richness right. Now, in our calculations, we're going to make ions. We're going to add electrons. So we wanted to check to see if the calculations work with charge systems. So what we did was measure the photoelectron spectrum. And what you do here is get the molecule in the gas phase and expose it to monochromatic radiation, helium-1, which is about 20 eV. That knocks off an electron from the valence shell. You measure the kinetic energy, subtract the energy of the photon, subtract the kinetic energy from the energy of the photon, and you get essentially ionization energy going, perversely it's plotted, going increasing from right to left. But anyway, there are various peaks. And this is the lowest ionization energy, the HOMO of the system. This is the calculated species. If we take an electron away, this is the cation or cation radical. And you'll notice their geometry changes. And so this means we have to look at the adiabatic ionization, which is the onset here, shown here. Right here is the adiabatic ionization. That arrow is what we calculate for the difference in energy from here to here. So again, excellent agreement. So what is the mechanism now if we do the calculations? There's our starting material. If we add an electron, this is what we get. We break the iron-sulfur bond or greatly elongate it, and we rotate around the iron so that this carbonyl can bridge. That was very important that we see this molecular reorganization because that will help explain why it's so easy to add another electron. Because of this molecular reorganization, we now have a LUMO that's lower in energy than the starting LUMO. We add a second electron at potential less than that. I don't have the values shown here, but you can see this in the calculations. That generates this dianion, which is after protonation, the pKa of that is about the same as acetic acid. So there's an equilibrium in which we get the protonated species. And it turns out, by calculations, you could have protonated on sulfur, at iron. Turns out you form a mu hydride, as shown here, hydrogen bridging two irons. Now that's a metal hydride, and what we would have liked to have happened is that react with a proton and generate molecular hydrogen and go back to the starting material, and that would be the catalytic cycle. And turns out that this is not hydridic enough to donate H- to H+ and generate hydrogen. So to make it more hydridic, we have to add another electron. This electron has to be added at -2 volts. Once we add that other electron and we have a protonated dianion, this reacts immediately with acetic acid to generate hydrogen. So with the insight that this mechanism provides, it's telling us what we really want to do is increase the electron richness of this system. Could we put on substituents, let's say on the benzene ring, that make this more electron rich so it'll be a beta hydride donor, and we can get this other catalytic mechanism at potentials close to the thermodynamic one, rather than having to go to -2, half a volt more negative. So here's a result of some of those studies. The idea is very simple. Hydroxy groups on benzene rings are known to be electron donating by resonance. So it's relatively easy to make the dihydroxy compound. We can make a variety of derivatives here, but anyway, we make these hydroquinone derivatives. And we look at the electrochemistry, so here's a list of them. And here's the reduction of the catalyst itself in presence of acetic acid. We generate hydrogen. But this is the benzene one without those OHs. And you can see they're poorer catalysts. They're not as good as the benzene. Well, why is that? Well, we thought that maybe the problem was that the hydroxy group hydrogen bonds. And hydrogen bonding to sulfur is an interesting area. People in general will say that hydrogen bonding, or at least Pauling's description of hydrogen bonding, was that it was essentially electrostatic. If you had a very electronegative atom, say oxygen, that you'd set up a big dipole in the OH bond, and you build up a lot of negative charge on that oxygen, and you could form this hydrogen bond. So fluorine, oxygen, nitrogen, very electronegative, would do it. Sulfur shouldn't. It's not very electronegative. Well, apparently, all the features you find in hydrogen bonds, you find with sulfur. That's because of polarization. And in fact, if you look at geometries shown here, you also see a geometric effect. So the lone pair on sulfur is coming out towards you in this geometry. The hydrogen can't hydrogen bond. If you rotate it, now the p orbital is pointing directly at the hydrogen. So this provides a hydrogen bond, and it's suggested to be important in the mechanism of action of galactose peroxidase. If you increase the charge on sulfur, you get this electrostatic effect. That could be done by resonance, or more importantly, charge assistance. If you make the S-, now you have a more negative charge here. You can hydrogen bond with, let's say, OH. And that's, in fact, what we think is happening. That is, as I already mentioned, you add electrons, you cleave that bond, increase electron density when you make the dianion. Is that true, that there'll be better hydrogen bonding here? Well, again, we look at calculations. And if you have both OHs pointing down toward the sulfur, that's the most stable system. If both of them point away, no hydrogen bonding, that's a lot higher energy. If you have one of them down there, it still stabilizes it. So if that's a problem, those OHs, how do you get rid of it? Replace them with methyl groups. And shown here is one of the hydroquinones. This scale is the same as this scale. And you can see with the dimethoxy compound, enormous amount of current for hydrogen production. Here's the methoxy compound with the benzene, and you can see it's even more active. This is an extremely active catalyst. Unfortunately, the dianion after protonation is still not hydridic enough to directly react with acetic acid, so we have to add another electron. But we're continuing these studies to see if we can actually get something that might be even more effective at increasing electron density at the dianion stage. So the last thing I want to tell you about is this idea of potential inversion. We thought that that is important from a chemical point of view, but you also may have noticed that in the enzyme, we have a bridging carbonyl. And so it obviously is important in the enzyme. And so we wanted to study this more fully. And furthermore, when you have different size bridges between the sulfurs and maybe different atoms here other than carbon, it's been reported, the literature is very confusing. It's been reported you either get a 1 or a 2 electron reduction, and sometimes with the same compound. So we studied this, and what we found is something rather interesting, and that is when there are 2 carbons here, the timing for the process I'm going to describe is just right to see the following. That is, now we're going to scan the potential in a negative direction and then reverse the scan. And here, when we go at 20 volts per second, relatively fast scan rate, we see this curve. As we go to slower and slower scan rates, and here it's 20 millivolts per second, you can see that now we get the peak here, and then we reverse the scan, we get the reduction, now the oxidation. This is a 1-electron oxidation. This is a 2-electron oxidation. So you can go, depending on scan rate and also depending upon the bridge, from a 1-electron to a 2-electron oxidation. Why? What's going on? Well, in the 2-carbon bridge system, it turns out to be extremely fortuitous, as you saw. And calculations now show that when you add 1 electron at this potential, that is the calculated potential, you get this anion. And if you look at the anion, compared with the starting material, there's no reorganization, no rearrangement. And so, as we said before, to add a negative charge to a negatively charged species would be electrostatically difficult, and you can see the potential becomes much more negative. On the other hand, what we find by calculations is that this can rearrange to give the rotated iron, and this is beginning to bridge that rearrangement that we talked about before, and now that species reduces at a potential lower than the starting material. We get our potential inversion. So with the electrochemical time scale, cyclic voltammetric time scale, we're in the right range to see this. That is, if we're going too fast, we can't add the second electron, we only add 1. If we're going slowly enough, we get the rearrangement and add the second electron. So this provides then more chemical insight into this rather interesting process, which may be important in the biochemical system, and also, as you saw, it's important in generating hydrogen. So finally, what I'd like to do is acknowledge the people who have involved in this work. There's a collaboration with Professor Evans, who's an electrochemist, Professor Lichtenberger, who's a theoretical inorganic chemist and also photoelectron spectroscopist. These are the postdoctorals that have worked on the program. Dr. Noriko Okamura is back in Japan in a teaching position. And these are the PhD students that have been involved in the project. And I'd like to thank the U.S. National Science Foundation for very generously supporting this project. It's a special program that National Science Foundation had, collaborative research in chemistry. And as you can see, we have, so I'm basically an organic, organometallic, synthetic chemist. We have a collaboration between a rather diverse group. And in chemistry, collaboration is not very common, and clearly is important to attack big problems such as the ones that we're attacking. So there has been an interest in National Science Foundation to support collaborative research. You do that here, but it's not, in the US, not terribly common. So these are the people that, a picture of the people that, there's Noriko, that are involved in the project. So that's Dr. Lichtenberger and that's Dr. Evans. And I thank you very much for your kind attention.